and then compare and see where we can see better to try to
It's
decide.
maybe better idea to do per class instead of, because now we have one system and then
Yeah, no, it's the same system.
Okay.
It's the same system, only that the camera you face whatever. This is recording my voice and in the same way, and it's capturing what the camera looks like. In what? Well, no, is that correct, Jaime? Now you are capturing the screen, the computer.
Yes.
If I switch to right here, instead of that, you need to capture the image from the camera,
Yes.
which we can use his, or you have one or not.
The ones that we have aren't very good.
Aren't very good.
The phone is much better.
Okay.
Bars blinks let us use it.
So for the second half, we might try to switch to do that, but the same software is okay. We open the same software. All it changes is what is the source of my visual. Okay, so you see why I didn't want that. Okay, so the idea in the course is, after establishing a little bit the ideas of probability, and by that I mean the conceptual way in which we will calculate probability. I'm not going to teach a course in probability. I'll give you teasers and problems in probability for you to think, which might sound to you more like these teasers or puzzles that people list, because I am not trying to teach you a formal course in probability. I need probability as a tool. But after we define that and we learn what we mean by counting states, etc., what I will do is use probability to build the concepts that are the basis of thermodynamics, which are temperature, energy, entropy, and so on, but define them just counting states, the way that was not done by the people who developed the ideas of thermodynamics, who defined concepts out of nowhere. In thermodynamics, you say, well, temperature is if something is hot or cold. But they don't say those words. They say temperature is what you measure with the thermometer. That's the actual definition that the theory of thermodynamics makes. It's the only branch in physics in which we define something by the measure. Imagine if you would say that space is what we measure with a ruler, but that's what they do in the thermodynamics. They say you find some material property that changes when something is hot or cold, and you build a scale. You put it in freezing water, and whatever that property is, you call it zero. And then you put it in boiling water, and whatever that same property, maybe the length of a ruler, maybe the pressure of a gas, whatever you pick as your property, what we call a thermometric property, that we will call temperature 100, and then you interpolate. That's how thermodynamics was built, using this very naive concept. Thermodynamics is what a thermometer tells you it is. Temperature is, and based on that you build all the rules, what happens when you put systems in contact, how much the heat changes, what processes take place in nature or not, etc. So I keep going, right?
The audio is working, but the visual isn't working.
Okay, good. So that was the naive concept, and based on that they built. Based on that and thinking of how machines work and things that you can see with your own eye, the theory of thermodynamics was built. I am not going to do that. I am going to build statistically those concepts. The idea is that I will start looking at how in a system we count how many states are, and when there are many of them, in which state the system will go, which states have the highest probability, and based on that, how we define the exchange of energy in systems based on the ideas of probability, and based on that, we will define the idea of entropy, which is nothing else than the logarithm of the number of states. So we are going to build all these concepts just in a statistical way. Once we have a basis on that, then we will actually try to do a little bit of the first successful problems to which this idea of counting states was applied, which is what we call kinetic theory or kinetic theory of gases, which is the development in physics that Boltzmann was responsible for, which is trying to apply this idea counting states to try to obtain some of the basic laws, in particular the ones of the law of gases, for example, to explain why these laws that people knew for 300 years, that if you take a system, a gas, and you squeeze it to have the volume, the pressure will double, or things like that, or if you squeeze it, it will absorb a certain amount of heat. So explanations to these things in terms of the motion of molecules was the first indication that there was something to representing the microscopic world through counting microscopic states. And so that part, which is what developed in physics between 1880 and 1910, I would say 1920, we will try to give you a glimpse of the principal problems that were done there. After that, I will go back to thermodynamics, but now informed, I will try to build a little more formally than you did it in elementary physics, or a little more formally than you will learn it from the elementary textbooks at the beginning of the course, and try to build exactly how you build, how you define entropy in terms of machines, etc. But now illuminated by what we know about the underlying microscopic element of that. And once we got that, and with the theory of ensembles that I will present along the way, we can start applying it, and this will be the second part of the course, to different situations. A gas of electrons, a gas of photons. The situations in which really we need to understand properties of systems using statistical properties of elements. So that part is what normally in many courses would go in a second semester of a course, because it's applications of statistical physics. But I believe we will try to cover at least the two or three principal ones, gases of photons and gases of phonons, and perhaps gases of electrons. And then some of the others we will cover using the possibility of you preparing special topics. As I mentioned already in the syllabus, I assume you looked at the syllabus. Before I even write, let me bring it here, so you have it. Closing this, but if I open another browser, no, I have a browser for Canvas here, right? Canvas here. Let me see if I can show you here. I'm sure most of you must have seen it, but just in my computer is smart enough and doesn't require that, but this one doesn't. So let me see.
There are 3 books.
No, I will speak about books in a second, but I need to tell you what the course would look like, because different books will play different roles in this course. Syllabus here. So, I mean, I believe I put it in my USB, but you can look it up here. I mean, these are the technical stuff, but if you look here, I will come to the textbooks in a second. I say that mostly will be lectures and examples that I give, homework problems. Homework problems here are different from problems you did in other courses. They are longer. So an assignment with 8 problems is already a very long assignment here, because they require mathematical elaboration, most of them. Not perhaps if I give you at the beginning a list of problems in probability for you to wet your toes a little bit in probability, but if we are discussing real systems, particularly thermodynamics, these require mathematical sophistication, nothing that you can do by answering or checking things in WebAssign. You will have to do the problem, write them down. If your handwriting is sort of acceptable, it's okay if you give it to me, but if your handwriting is not, and in many cases it's not, just use some software, use whatever you want, type in, I can open any file. So, but homework will play a role, but you will see I'm not going to give you homework every class. I will develop a subject, 2-3 classes, and after 3 classes I'll give you an assignment that you will have some time to do. But at the same time, I might give you, as it says here, a few projects that might require, and this will be sort of part of the homework. Go to the computer and calculate. For example, if we are discussing random walks, I might tell you tell a random walk. You do a random walk of 10 million steps and tell me what is the average displacement, what is the average quadratic something. So I will ask you a little bit for you to do the, so if you want to see my face, I will stand here. And as I said here, at the end of the semester, I will assign subjects that will be more applications of some of the topics, applications of the knowledge we develop. So you probably will not be, well, you can tackle them whenever you want, but probably you will be better off tackling them towards the end of the semester when I had the chance of deal with ensembles, deal with showing you a couple of situations. And I believe I have a list here, let me see if I can open it here, of possible topics that I typed this morning. But they are by no means an exclusive list. I can imagine many more topics that I come up with. Okay, here I believe I type. Let me see. No. I thought I had written.
Yeah.
Here, exactly. Here, probably. I have it. Yeah, I typed a few final topics that just occurred to me. I'm sure you can find many more. But just to have an idea what sort of things I might ask you to do. So probably, although I will cover some Bose gases, particularly gasophotons, as I told you, and gasophonons, perhaps the application of that to condensation problems, in other words, to liquid helium, will be something that I will not cover. In the terms of theoretical thermodynamics, I might only cover here properties of ideal gases. Real gases, which is a wonderful chapter of thermodynamics, in particular the van der Waals gas, that was the first model of a gas non-ideal that was solved around the 1890s. I might not cover, I might let someone to explain that. Some phase transitions in statistical mechanics. The main example, somebody told me that you had some familiarity with the Ising model. So that will be, it was the first model that was exactly solved in more than one dimension in statistical physics. I would say, or many people would say, it's the only model that was ever solved, because all the other models that people solved exactly are slight variations of these in 2 dimensions. In 3 dimensions, so far, nobody solved any model in physics. So all we have is many methods to approximate the solution, but solving exactly, and it will be clear in the context of this course what do I mean by solving a model exactly. The only case we know is the Ising model in 2 dimensions, which imitates ferromagnetism. So that would be a wonderful subject. This course will not deal with non-stationary phenomena or transport phenomena. It will be equilibrium. It will be thermodynamics of equilibrium systems. Non-equilibrium thermodynamics is a complicated subject. It requires a special course, but at least the introduction which was written by Boltzmann around the 1890s with his equation of transport. Somebody can look into that. Oh, the Ising model I already mentioned. Another is how do you approximate in the computer many of the models of statistical physics. And one of the most powerful methods is called the Monte Carlo method, in which you can simulate systems, and so somebody can look into that. How do we simulate the system using Monte Carlo? How do we extract information, etc. So these are subjects that are quite advanced. And as I am telling you, they would never be part of the first semester of a course in statistical physics, but somebody might want to look into them in the future. So I just wanted to present them. So I believe I gave you a feeling of what are the main areas that we are going to cover. So, sorry, okay. So when I want to write, I ask you and you will move that. So if I click here, I can go from the camera to that. Okay, good.
Now you start writing?
Oh, I will start writing, yeah.
Okay.
So I wanted, with all of that, just give you a feeling of what sort of things we are going to cover. So the first part, as I'm telling you, is mostly to develop a language. That means, and the language of statistics and how we count states, because the main ideas of thermodynamics, in the modern sense that was built by Boltzmann, was a problem of counting states. So the first thing we need to learn is to count them, to build the statistical concepts that the people in statistical mechanics try to explain of the ideas of thermodynamics, is to build these mathematical concepts. So I will devote the first couple of lectures, probably perhaps a little more, to actually develop some theory of counting states. How do we know what is the distribution of the different states? Try to convince you why systems do the way they look. Because after all, you understand that when you look at a system, you look at a gas, it's not in one state. The molecules are moving and every microsecond is in a different state. Still, we speak about the properties of systems. So that means that there must be some sense in which, out of all these microscopic systems, in which a system can be and we describe as a certain microscopic reality, there must be certain distribution of states there that allow us to predict property. Because after all, you can predict what will happen. If you heat a gas, you can predict. If I give it this amount of heat, what will be the final temperature? I can do these predictions, in spite of the fact that all I'm doing is changing the statistics of things. All I'm doing when I'm heating a system is putting one of the walls hotter than the rest, and so particles, when they knock against that wall, they bounce back, but it bounces moving a little faster, and so eventually those will collide with somebody else, and that somebody else will move a little faster. Somehow, out of all this complicated microscopic world, we manage to find and describe microscopic laws. So that means that behind the theory of the statistics of how many states they are, and I will devote the first lecture today to convince you that there are many of those, I want to build some of these statistical tools that I will need. Although today I will spend some time developing a little bit of mathematics and integration that we need to do eventually. So there are lots of integrals that appear in statistical physics that are so standard that in any textbook of statistical physics you look, and I am aware that they didn't speak about text, I'll come to that later. After the break, we can come back to that. So there are, as I was saying, there are certain statistical tools, statistical integrals that appear over and over. So you pick any book in statistical physics and they will have some appendix in which they say, let us calculate all these integrals because we will need them. You cannot describe the distribution of particles in a gas, which is a very big part of kinetic theory. That was the big advance that Maxwell introduced in physics, besides obviously the laws of electromagnetism, was finding the distribution of the velocities of molecules in a gas. And in order to do those things, you always encounter the same integrals. So I would spend some time getting them out of my way, your way, so whenever we need them, we already have them. So before I go to that, let me just spend some time arguing about why do we consider even a statistical approach to the world, and why don't we actually are satisfied by using the laws of mechanics that we understand, or we believe we understand so well, to just count how molecules collide and where do they go, etc. And in order to appreciate why we don't do that, you need to understand that our microscopic world is made out of many molecules or many particles. But when I say many, I mean that the number n that will appear in this course as the number of particles in a system is always a very big number. And it's not enough for me to convince you that it's big. I know that you know what big means as opposed to small. I need to convince you that this is not big. This is bigger than anything you ever considered before. So I will spend some time telling you a little bit. So when you have a system, I don't know, the size that can fit in this box. Normally you have pretty much Avogadro's number of molecules. So that requires an explanation. In around 1811, there was a chemist called Amedeo Avogadro who came up with the idea that equal volumes, or equal masses of matter would have the same number of molecules. So there was a number that told you how much matter was there. Remember, this is a century before anyone had any idea of atoms, so he couldn't know how many. He said there are many. He believed firmly that there were atoms around, but he couldn't have an idea. So Avogadro never had even a clue of what Avogadro's number was. So, but now we know, and that in itself is an interesting story. When we discuss kinetic theory, I will tell you how we got the idea of Avogadro's number, but that appeared in physics around 1875, 1880, and all the ideas of kinetic theory had to be developed to just get a hold of that number. So, first of all, let me tell you, there was something that Avogadro and even before him, the century before him, people know. People had an idea that if you have matter is made out of little molecules, there are many of them. So what did they say? They say the following: well, after all, chemists know for a long time the rho of all the elements, how many kilograms per cubic meter of anything there is. And you open the table of chemistry, and people know that a kilogram of lead has a volume of this much, and a kilogram of water has a volume of this much. The rho of water is, for you to have an idea, is around 1,000 kilograms per cubic meter. So those were things people knew. And that if you take a solid, rho of, I don't know, iron, will be 5-6 times bigger, 6,000 kilograms per cubic meter. But if on the contrary you take something very ethereous like air, the rho of air is around 1 kilogram per cubic meter. So the idea, we know what happens. The molecules in that in air are farther away than the molecules in water or in iron. They are less compact. So that's why in the same volume we have a much smaller mass. So that was an information that was available to them. But what can you do with that information? Well, the idea was the following. What they intuited, and it was not a wrong intuition, said, Well, obviously, in a gas, the molecules are not that close to each other. How do I know? Because I can squeeze it, and I can take a gas and make it 10 times smaller, and that works. Okay, that's calling compressing a gas. But liquids and solids are not like that. You try to compress it, and the compressibility, later on we might define what the compressibility is, it's very high. So you cannot squeeze them, essentially, or it's very hard to squeeze them. So the assumption is that when you have a solid, the atoms are packed solid. They are one next to each other, and that's why you cannot squeeze them more. So they said, well, if the atoms are very close to each other, you assume that if in a mole you have this number that we have no clue what it is, which is the number of atoms in a mole. By the way, you heard about Avogadro's number, right? So that was a construction that chemists did. They said Avogadro's number is the number of atoms that you have in 2 grams of hydrogen, or the number of atoms you have in 12 grams of carbon. They discovered that different things combined in fixed proportions. So they defined that, say, if you take 12 grams of carbon, that we will call a mole of carbon. The number of atoms there is what we call Avogadro's number. In many countries you will see call it Loschmidt number, because Loschmidt was the first person who had an idea about this, but doesn't matter. So, but anyway, if we get a mole of a substance, we have these atoms, and if we assume that the atoms are sort of packed, the volume they will occupy, if an atom has dimension d, n Avogadro d cubed will be the volume this mole will occupy. Okay? So I am assuming that they are relatively compact. So if I take a solid, pretty much number of Avogadro times d cubed will give me the volume of that mole. So if I multiply by the density, it will give me the mass of a mole. And the mass of a mole is what chemists have been calling since the 1700s the molecular weight of the object. Okay? So, and remember, these things were known, and the molecular weights were known. So indeed, n Avogadro d cubed was a known quantity. So you could list it because, I don't know, for water the molecular weight is, whatever is it, 18 grams. So 18 times 10 to the minus 3, I'm not trying to teach you chemistry here. And the rho of water, we said, is 1,000 kilograms per cubic meter. So out of that, you get the number, and this is kilograms per mole, and you divide kilograms, you make meter cubics per mole. You get the number of atoms there, correct? So that means that this quantity, Avogadro's number times d cubed, was sort of known since the instant the idea of speaking in terms of moles appeared. The only problem is that you cannot know this. So if you know the size of an atom, you know Avogadro's number. And if you know Avogadro's number, you get the size of an atom. Okay? The problem is, as I told you, that Avogadro and the people that developed thermodynamics had not, well, they were not even convinced that atoms were real, but even the people who were convinced, they didn't have a clue. So they needed somehow some other source of information to get a hold of what Avogadro's number was, or what is the scale of an atom. Is an atom something of the size of a micron? So 10 to the minus 3, that would give me, well, by the way, this gives me 10 to the minus 5, right? So roughly 20 times 10 to the minus 6, or 10 to the minus 5. Roughly speaking. So this is 10 to the minus 5, give or take, okay? So if the size of an atom is a micron, this is 10 to the minus 18, Avogadro's number will be 10 to the 13. If the size of an atom is 1,000 times smaller, Avogadro's number will be 1 billion times bigger. Nobody had any clue. I mean, they guessed that the size of an atom was not a millimeter because they had eyes, so they didn't see atoms around. I mean, they had microscopes by that time, by the late 17th century, early 18th century. Leeuwenhoek came with a microscope, but they didn't have any clue what was the atomic scale in order to have a clue of what was Avogadro's number. So when we discuss kinetic theory, I will tell you the experiments they did that gave them another relationship between Avogadro's number and D, out of which finally around 1880, 1885, we found out the size of the atomic scale. Actually, 20 years later, we got an experimental idea about the atomic scale because Bragg came with a famous experiment that you might have heard of diffraction of X-rays, and we established that this number is of the order of 10 to the minus 10, which is what we now know. And that means that Avogadro's number is 10 to the 24, which is what we now know. But this was an idea that slowly entered physics in the 1890s, 1900s. So I don't want to jump the scale. But having said that, we know that. Now we know that Avogadro's number is 6.02 times 10 to the 23, give or take. Okay? So I want to convince you how big a number this is. That's my first task. And so any book in statistical physics goes through some argument to convince you about that. I picked one, you can pick another one. If somebody finds a better one, bring it, I would love to hear it. So mine would be the following, and that was the way I was exposed for the first time. So you see, one of the problems that is a leading problem in statistical physics is the laws that tell you how atoms interact are very Newtonian laws. Particle A is here, particle B is here, I know the potential of interaction, I can the machinery, I can tell you a little later where this one will be and where this one will be. In other words, you give me all the initial conditions of a problem, you tell me the interactions between the particles, there is a machinery that Newton gave us and we perfected that tells us what will be the state of the system in the future. Or the other way around, you give me the state now, I can crank the machinery backwards and find what was the state of the system 3 seconds ago. So in principle that's fine, but the thing that the people in statistical physics knew and dealt with is that the physical world is not reversible. We know that's the basis of thermodynamics, the idea that processes go in one direction and one direction only. If you have a tank of water and you put a drop of ink there and you wait 10 minutes, the ink will dissolve there, and there is no process in which ink dissolves in water will come back and congregate again in one drop. If you have a system in which half of the system are molecules at 300 degrees and half are molecules at 100 degrees, you put them together, you wait a little bit, and the whole system will be at 200 degrees. And there is no system that we can come up with where we put molecules moving, having a temperature of 200 degrees, and I know that I'm not being precise, we didn't define temperature, etc. But understand the idea behind that. We put a system at 200 degrees, it will never happen that all the molecules very hot will congregate in one place and all the cold ones will congregate in the opposite. Another one, you have a container full of gas here and a container evacuated here. This is vacuum and this is a gas, and you put the valve here. This is gas and this is vacuum. You open this, and after a very tiny fraction of time, there will be as many molecules here as here, and you can detect that by measuring the pressure. There is no way that if you put a system like this and you open the valve, suddenly all the molecules will go to the right and the other half will remain empty. That doesn't happen. So clearly, there is a direction in processes in nature. That's the content of the second law of thermodynamics that we will explore. So the question was, where does it come from? If you try to explain things in terms of the molecular motion and the equations of motion are Newton's laws that are perfectly reversible, and if this molecule can come from here to here, also can go from here to here. How come that in this system it goes always in one direction and never in the other? So this is one of the leading problems, still not solved in statistical physics. Where does the irreversibility that we will describe in this course and measured by the second law of thermodynamics come from? So one thing that, you know, the professor I had when I was exposed for the first time to statistical physics told me is, well, there would be a way to know. You take the molecules in a little substance of matter, 10 to the 23 molecules, you register, let's say, or you come up with the initial positions, you crank the machinery, and you look 2 seconds later, where do they go? And you find in which state they go. And you can find if they go to all possible states or not, or only certain states, like this one, where they mix up, and not in the other state. So it would be a wonderful thing if we could settle all the arguments that still philosophers and physicists have about thermodynamics by actually solving a system of 6 times 10 to the 23 particles, knowing the initial positions, the initial velocities, cranking the machineries, and getting the final position, the final velocity. First of all, you will tell me, well, solving 6 times 10 to the 23 coupled equations is very hard. You are not going to do it in your laptop. Okay, but let's imagine that this project is so important that all the resources of our planet are given to you. The biggest supercomputers, you convince Google, you convince everybody, and they tell you, okay, we'll run the problem for you. So let's say you do it, and you find these particles, and you find after, although it's ridiculous even to think that this could happen, you find where the 6 times 10 to the 23 molecules are after 5 seconds. So what do you do with that? Well, you want to look. So let's say that you decide, well, let me get a printout of the coordinates of these particles. And then I will do some study, where they are they in multiple. So let me try to do a printout of 6 times 10 to the 23 particles. So I will write the first particle is at 3.4526, comma, 7.1629. The second particle I will write here is whatever. So each particle, let's assume I have 5, 6 digits of precision, the best I could. Obviously, I'm writing in the board, my letters are very big, but imagine that you print it as small as you can so that you can read. So give me a number. How many of these can you print in a row of paper, in a sheet of paper? 20. Okay, let's say you print 20. And then you put a nice line, a second line, and a third line, and a fourth line. So in a page, you can put 1,000 particles, the coordinates of 1,000 particles. Okay? And this is with small print. So it would stretch me that I am old and my eyesight is not as good, but perhaps you can read. Okay, you get those 1,000. Well, now you need the next 1,000 and the next 1,000. So when you get a million, this is a thick thing like this. So now you have like a book. You have a book that all it has is the coordinate and positions of 1,000,000 particles. So then you go and you print another book with the next million. So let's say you get a nice shelf here. And you can put how many? 50. 50 books in that shelf. So we are now at 50 times 10 to the 6 particles. And of course, we don't need one shelf. We will build shelves from floor to the bottom. So we will build 10 shelves. So we will get, so this is 5 times 10 to the 7, 5 times 10 to the 8 is a shelf full of coordinates of particles. we need more. So what we will do is we'll empty this room and remove all these chairs and put another row here, and another row here, and another row here. So we'll build a room full of shelves. So we will put in this room, how many you want to put? 20. 20, you will have trouble moving through them. But let's say 20. So this is 10 to the 9, okay? No, 10 to the 10, sorry. So we fill this room completely. There is no room for anything. There is no room to put a chair or anything, and we put 10 to the 10. Clearly not enough. So since we have all the resources, we convince the president of the university to empty the university and give us all the rooms. And so we have now, what, 500 rooms. Okay, 500, I don't know if we have 500, 100 rooms in the university. So we fill the university with coordinates, and we are by 10 to the 12. So clearly it's not enough. So now, or let's say this is a big library, a library with 100 rooms. So we get all the libraries in the city to collaborate with our project, and we have like what, 100, 500 libraries. So we might get 10 to the 15, and we already exhausted all the area that we can put things in the city of New York. So now we need to go and convince people in other cities and in other countries. I don't know, how many cities like New York will we convince? 1,000 cities like New York? We are still around 10 to the 18. So we didn't get even 100 of 100% of the coordinates of those particles, and we filled our planet with numbers. Okay, so obviously 10 to the 23 is too big for us to try to look at particles. I will show you now that for the standards of statistical physics, that's a very small number, that we will deal with numbers that are much, much bigger. And when I say much bigger, are numbers that compare with that, this number is nothing, and we will come to that. But I already wanted to show you that 10 to the 23 is a very big number, that you don't deal with 10 to the 23. Our best molecular simulations are 10 to the 4, 10 to the 5. Of course, you can tell me you don't need to print those, you can store things in disk, you can tell me many things. All I'm trying to give the sense to you is that 10 to the 23 numbers, there are not enough paper, even if you decide to, as the president of Brazil is doing, to simply raise the whole Amazon forest and use that to print paper, you cannot print 10 to the 23 numbers. So the numbers we deal in statistical physics are huge. That's the first lesson I wanted to give you. Just to give you even, since I told you, we are going to learn now that in statistical physics, the game is to count states. And that means even another level. Imagine that you have particles, our 10 to the 23 particles, and what happens is that particles can be in certain states. Let's say, to keep it simple, 10 states. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So one particle can be here, the other can be here, each particle is in a state. And the energy of a state will be given if this has energy E1. We'll do calculations like this. So I am just giving you a feeling. Okay, E4, E5, etc. So we have a whole sequence of states, let's say 10 states, and you want to describe a state. A state is determined if I tell you particle 1 is in this state, particle 2 is in this. So each state is a vector with 10 to the 23 coordinates, telling you the first particle is in state number 3, the second particle is in state number 7, and so on. So even if we have something as simple as 10 states, and those of you who studied quantum mechanics know that the system doesn't go to 10, goes to infinity, but let's say just to 10, well, you have to give me 10 to the 23 numbers to describe one possible state of the system. And in statistical physics, what we need to do is not to write one state of the system. We need to count all the possible states of the system to find out which probability each one has. So what we would need to do is to calculate how many states of a system of 10 to the 23 particles is there. And well, you can do the calculation very easy. If the first particle can be in 10 possible places, and the next particle can also be in 10 possible places, and the next particle can be in 10. So you get 10 times 10 times 10, 10 to the 23 times. Or in other words, 10 to the 10 to the 23. Okay? This is counting states now. Now I'm not counting particles. I want to convince you that this number is big. Just to tell you how big, I'm not going to tell you I want to print all the states, because I told you already that to print one state will take me all the books. So imagine if I need to count states. So just let me do an exercise. So 10 to the 23, anyone has a stopwatch? Yeah, use your clock. Tell me. I will write 10 to the 23, the number 10 to the 23 for you. The number of molecules in a mole. How many are they? Starting now. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, how much did it take me? 30, 40 seconds. Well, I am very slow, but but let's say, so you are saying that I can put 2 numbers per second, because I wrote 23 zeros. 2 numbers per second. Okay, with some training, you can do better than me. You can put 5 numbers per second. Okay, so, but this, dear students, is the number of molecules in a mole. Now I want to write the number of states in my system, which is this one. So I want to write this number. So this is what? A 1, and how many zeros? 10 to the 23, right? 10 to the something is a 1, and that number of zeros. So I need to write that. So you tell me that I can write 2 numbers per second. Let's say you are better than me and you write 5 numbers per second. So this is the number in a minute, this is the number in an hour, this is the number in a day, this is the number in a year. If I don't stop, I don't eat, I don't sleep, I don't do anything. This is the number of zeros I can write. 36, 20,000, 500,000, 336, this is 15 million, around 15 times 10 to the 6. This is the number of zeros I can write in a year if I don't stop. If I devote myself a century, I would go to this. Okay, this is if I spend a century writing a 1 and zeros.
It's actually worse.
I would go to this. So imagine, in the age of the universe, how many zeros can I write? Assuming, if you believe in my chronology, yours might differ. I am not going to fight about ideological issues, but if we believe that the world has 13 times 10 to the 9 years, 13 billion years, okay, give or take. If this is the number in the year, I would be by writing 10 to the... So if I devote the age of the universe to write, I cannot even write the numbers, let alone enumerate them. Just tell me how many they are. Write the number for me in the board. It would take me the age of the universe. So you see that we are dealing with very big numbers. That's what I want to impress on you. Having said that, let's stop a little bit the fun and games, and let's do a little bit of what I call fun and games that might not be your choice. So, one of the first things that you learn is that when you deal with big numbers, the way to deal with them is using logarithms of big numbers. Logarithms are the main feature of this course, because everything, well, let alone, please, in your computer, type Boltzmann and put Boltzmann grave. Well, probably it's in the cover of any book I might have here. Boltzmann grave, this is Boltzmann's grave in Vienna. It says K log W. So he must have believed very strongly on the formula to put it in his grave. So this is the first grave I found with the logarithm on it. So logarithms are a huge part of what we are going to deal with here. So we need to learn to calculate logarithms. The other thing that we will need to learn is to calculate factorials. Factorials play a big role here. Why? Because, well, when you are trying to calculate the number of states, let's imagine that, let me give you the trivialist example. I want to calculate the energy of a system, and I have the energy, this is 0, 1, 2, 3, and I want to calculate the energy, the states that have total energy equal to 0. That's very easy. If I have four particles, it's very simple. There is only one way of accommodating here 4 particles and the total energy is 0, to put the whole of them here. But if the total energy is 1, now there are more states, because I can put one particle with energy 1, the other 3 with energy 0. And now I have 4 choices, right? Because the first particle can go there and the other 3 here, or the second, and so I have 4 states. And if the total energy is 2, we'll actually do the math a little later. If the total energy is 2, now I have several ways, because I can put one particle of energy 2 and all the others 0, which gives me 4 ways, but also I can have 2 particles with energy 1 and the other 2 with energy 0. So what am I trying to go to? To the fact that you will need to calculate how many ways of choosing 2 elements out of 4. And that's called the combinatorial 4-2, for those of you who didn't take a formal course in probability, or 4 factorial over 2 factorial, 2 factorial, okay? We will need to calculate this so many times that we need to have the values of factorials, okay? If instead of 4 particles we have 10 to the 23, you will have something where you will have 10 to the 23 factorial divided whatever. So you see, calculating the factorials of big numbers will be part of our task. We will need to learn how to calculate big factorials. So what I did is I went to Mathematica and I told Mathematica to calculate. Oops. Did I destroy something? I said so. Am I okay? You see why they don't have to keep me close to important things? Okay, let me go to Mathematica. Here, I asked Mathematica to calculate some factorials for me to see how much I can do. Come on. Okay, this is the factorial. The first row is the factorial of 100.
That's one number?
Yeah, that's the factorial of 100. I told Mathematica 100 factorial, and this is the factorial of 1,000. Okay?
That's quite a big number.
All these and a bunch of zeros. I'm not sure if I'm moving the right way. And then I said 10 to the 23, which here you have the 23 zeros. I say, give me 10 times 10 to the 23. It already cannot do it. It tells me overflow. But I said, give me the factorial of 10 to the 23 overflow. Nobody can get you factorials of more than 1,000 or 3,000 or 5,000 or 10,000. Your computer might be a little better than mine, but you see, there is an issue here that we face. When you have very big numbers, we have to have better ways of calculating factorials and better ways of expressing things. So that's where my mathematics comes in, and I need to teach you there is a way. There is an approximation to calculate the factorials, which is the Stirling approximation. This was developed by the mathematician Stirling in the 19th century, and we all use it all the time. Again, you go to any book of probability, and you will have an appendix that says derivation of the Stirling approximation. So in order to do that, I have to teach you a little bit of factorials first. So that's where I want to go. So the first thing I want to teach is the following, that there is something to n factorial. n factorial, if you look in your books, will be this. Integral from 0 to infinity, right? Yeah. This is a very important expression, and based on that, we'll get the Stirling approximation. So I want to convince you that the factorial of any integer just can be obtained by calculating this integral. Anyone has an idea how you prove that? There are mathematicians here, so you should know.
Yeah, you have to plot it. The line.
No, plot it. Prove it. No. Here we are talking mathematics. This is not Professor Quilly joking around with numbers.
Human sum, maybe?
No, this is a simple induction. For 0, the property is trivial. 0 factorial is the number 1. And when you have x to the 0, is the integral of e to the minus x dx between 0 and infinity. And that is minus e to the minus x between infinity and 0. And the upper limit is 0, and the lower limit is 1. So this integral, I hope you know this integral is 1, right? So 0 factorial is x to the 0 e to the minus x. So now that we know it for 0, the next step is what you do always in induction. You assume that the property is valid for n, and using that you try to prove it for n plus 1. Let me do that. So I am assuming that this is valid, and I want to calculate x to the n plus 1 e to the minus x, integrated from 0 to infinity, and calculate what it is. Okay? And this is, how do you do it? You all did Calc 1, right? By parts. Okay, so this is, you call this u, you call this dv. So you have x to the n plus 1 minus e to the minus x, because this is v, between infinity and 0, minus, let me do it here, minus the integral of v du. V, the minus, and this is the v, so I get plus e to the minus x, times the derivative of this, which is n plus 1 x to the n dx. So this is simply 0, because in the lower limit e to the in the upper limit e to the minus infinity trumps any power there, so this is 0. And when this is 0, this is the number 1, but this is 0, so this is 0. So all you get is this, n plus 1 times the integral of x to the n e to the minus x dx, which we agreed that by the inductive hypothesis, this is n factorial. So what have I proven? So n factorial times n plus 1 is n plus 1 factorial. So that n plus 1 factorial is just the integral of e to the minus x times x to the n plus 1. So I assumed that the formula was valid for the case n, and I proved it's valid for n plus 1. So we have established this formula. All this work just to establish the first of many formulas that we'll need. This is an expression of the factorial. By the way, let me tell you a bunch of things. Those of you who are doing a course in mathematical physics, and I know mathematical method will do this, but let me show you that this leads directly to a generalization of the idea of factorial, okay? The idea is that you use this to define a function now, not just for natural numbers, but for any numbers. So let me do it. I define the integral of x to the n minus 1 e to the minus x between 0 and infinity. I define this as the function gamma. I don't define, Euler defined this as the function gamma calculated in the number n. Sorry, no, x is a variable of integration. This is an integration. This is gamma of n. So pay attention. I define it in such a way that if n happens to be an integer, gamma of n is nothing else than n minus 1 factorial. So the function gamma that is defined in that expression, gamma is such that if you calculate at an integer number, gamma of 7 is the factorial of 6, and gamma of 39 is the factorial of 38. But in principle, I can define it for now for any number. I can calculate gamma of 1.3. You see, because gamma of 1.3, according to that formula, so the main property here, obviously, is that gamma calculated of n plus 1 is n times gamma of n. Okay? That's the main property that defines the gamma function. You can define it through the integral, or you can define it like this.
So why is n all of a sudden no integer anymore?
Well, you can use it to define a continuous function for any number. But this will be true for the same proof I did before. Gamma of any number is the previous numbers times gamma of that number. So gamma of 1.3 is 0.3 gamma of 0.3. So you see, all you need to do is to define gamma between 0 and 1. And if you want to calculate in any other number, you shift. Gamma of 3.6 is 2.6 times gamma of 2.6, which is 1.6 times gamma of 1.6, which is 0.6 times gamma of 0.6. So if you define carefully gamma, or you get a table, or you get Mathematica to tell you what is the value of gamma for any number between 0 and 1, well, now you have gamma defined for any number. Actually, in this course, we will not need that many gammas, but we will need actually one very useful, which is the gamma of a semi-integer number. That will appear a lot, and you will see where it will appear. So, gamma of n, where n is an integer, we already know what it is this. Okay, now I want to calculate gamma of n plus 1/2. So of a semi-integer number, okay? And do I have it? Yeah, well, so as I told you before, let's say if I want to calculate gamma of 7/2, this is 5/2 times the gamma of 5/2 times the gamma of 5/2, which is in turn 3/2 times the gamma of 3/2, which is in turn 1/2 times the gamma of 1/2. So in order to calculate gamma for any semi-integer, I need to know just this. What is gamma of 0.5? That's what I need to know, and that will lead to the next sort of integrals we need to calculate. That we will calculate by definition. What is gamma of 1/2? By definition, is the integral between 0 and infinity of x to the 1/2 minus 1, so x to the minus 1/2 e to the minus x, or the integral of e to the minus x over square root of x dx. Okay, that's gamma of 1/2. So I need to calculate that one. Okay? So should I calculate now? Because that's already the Gaussian integral. But well, let me calculate. So I need to calculate this expression, gamma of 1/2. And then I will get the gamma of any semi-integer. Gamma of 1/2 is the integral of e to the minus x over square root of x dx between 0 and infinity. And okay, and that you do a change of variable, you call x, you call it t squared, so you get the integral still from 0 to infinity, because the square root of 0 is 0, the square root of infinity is infinity, but you get e to the minus t squared over t, because if square root of x, we call it no, x I call it t squared, square root of x I call it t, and dx is 2t dt. Okay? I am calling x squared, no, I am doing it the other way around, right? I am calling x, I am calling it t squared. Yeah, that's what I did here. X, I call it t squared. So dx is 2t dt, and so the t's go away, and I get the integral of e to the minus t, twice the integral of e to the minus t squared dt from 0 to infinity. This is the first Gaussian integral that we are facing in this course. Gaussian integrals are integrals that are e to the minus something times the variable square. We are going to discuss them a lot today, but just let me calculate this one, since this one is sort of emblematic, and I will use it to calculate later another Gaussian integrals. The way you do that is, this is a beautiful trick. You just take the square, this is twice the square root of e to the minus t squared dt times e to the minus, I don't know, u squared du.
Error function.
So I write my integral as the product of twice the same integral, and then I take the square root. I didn't do anything crazy so far, but this turns out to be something very nice, because this is twice times the integral of between minus infinity and infinity dt du e to the minus t squared plus u squared.
Isn't this like an error function or something?
Sorry.
Yeah, it's a sum of the sum.
Yeah. Well, the Gaussian integrals and error functions are very much related. But actually, let me do something. Think of this a little bit. Those of you who took Calc 2 must have seen that. Instead of t and u, call it x and y. What do you have? E to the minus x squared plus y squared, dx dy. So this is an integral over the whole plane of the function e to the minus x squared plus y squared, which is, go to polar coordinates, obviously, this is twice the integral of e to the minus r squared, and now I'm doing it in polar coordinates. So I am integrated from 0 to infinity dr from 0 to 2 pi r d theta. Okay, I switch to polar coordinates. R dr d theta are the integral in polar coordinates. In theta, I integrate from 0 to pi. In r, I integrate from 0 to infinity. Okay, I just switched my old problem to polar coordinates. Remember, I need to take the square root at the end of the whole story, so let me not forget. This integral is trivial, it's 2 pi, so I get 2 times the square root of 2 pi, because nothing depends on that. And this is the integral of r dr e to the minus r squared between 0 and infinity.
Now the original part.
And now, or you don't need to do that, r squared, call it u again, and say that this is 2 over square root of 2 pi. I put here a 2, and I remove a 2 here, and I put here a 2 here, and I get square root of pi, just, and I get the integral of e to the minus u du between 0 and infinity, and something I did wrong because I shouldn't have gotten the factor 2. The 2 should have gone away. These 2 should have gone away. I had a 2 coming from the fact that I multiplied that. Oh no, that 2, sorry. That 2 is the one I used to write the 2r dr. Okay. So I get the square root of pi only. The square root of pi remains inside. And this integral, of course, we calculated before, is the number 1. So the whole result is square root of pi. So this is our result. That gamma of 1/2 is square root of pi. Square root of pi, so, okay? And remember, let's go back here. Gamma of 7/2 was 5 times 3 times 1 over 2 times 2 times 2 of square root of pi. So you can immediately see that what you get is that gamma of n plus 1/2 will be the following: 2n minus 1, 2n minus 3, all the way to 1, and here on the bottom I will get 2 to the power n. Before I had 7/5, no, starting for 2n plus 1. 2n plus 1. Come on. Okay, 2n plus 1, 2n minus 1, etc. Okay, remember, for 7/2, gamma of 7/2 was 7 times 5 times 3 times 1 over 2 to the cube. 7/2, 5/2, 3/2, no, 2 to the 4. Okay, because I had 1 for each factor, right? Let me make sure I will have it right. 5, 3, of 7/2, no. Of 7/5 I start from the 5, okay. For 7/5 I start from the 5. And I have 2 to the cube. Okay. So I start from 2n minus 1, okay, and I have 2 to the n. So I get 2n minus 1 double factorial divided 2 to the n square root of pi. That's an important result. The gamma in any integer plus 1/2 is this number. Did I get it right? Is 2n minus 1 double factorial over 2 to the n divided, multiplied by square root of pi. Actually, that's all I need here? Yes. Yeah, that's enough. For the purpose of doing these calculations, it's enough. So let me just summarize my result. Gamma of n, where n is integer, is n minus 1 factorial. Gamma of n plus 1/2, still when n is integer, is 2n minus 1 double factorial over 2 to the n square root of pi. So the gamma of n are integer numbers. The gamma of n plus 1/2 are irrational numbers, square root of pi. Okay? So now, well, now it's a good time to stop a few minutes, but then now I am in position to calculate Gaussian integrals. Let me tell you what they are, so later we'll do the calculation. Gaussian integral is doing this. The integral to e to the minus alpha x squared dx between minus infinity and infinity. This is the sort of integral that appears a lot in statistical physics. Times x to the n. And so we will need to learn to calculate this for n equals 1, 2, 3, 4, and you will see that when you are calculating average of velocities or average of energies, it's always using this. Why is that? Because later we'll learn this is called the Boltzmann factor. The energy will be quadratic and you will have e to the minus something times the energy. So that's the reason why this sort of integrals will appear a lot. So this integral is called I sub n, and it's called the Gaussian integral of n for value n. So as I'm telling you, check any book, you will see that you have an appendix in which they teach you how to calculate these things. But you will see that now that I calculated the factorials, this will be very easy. This will take me no work. So I will do that after the break, and then we can start discussing physics. Okay, good.
I'm also going to discuss what chapter